Open up a script or a config file in a text editor and you'll be greeted with a structure that's readable. But open up something like a WAV audio file and you'll see nothing but gibberish. And this is the same for many other kinds of files like executables or images or videos. Clearly there is a logical structure, information is stored within these files. But how do you read it out or even create it? Well, that's what we're going to find out today on low-level JavaScript. Files formatted in this way are typically known as binary files, and they tend to pack information very efficiently by having a precise layout, compressing data, or otherwise encoding the information. But every file format has its own unique encoding, and specialized software is typically required to read, edit, or create them. For this episode, let's take a look into the WAV file format. It's a relatively simple format that usually encodes high-fidelity audio data, typically without compression. Because of this, the file size can easily be very large, and this is one of the reasons it's usually not used in everyday life. For me, the first step in understanding any binary format, or anything for that matter, is usually Wikipedia. Typically, you can find very detailed descriptions on how file formats are encoded there. But as it turns out, for the WAV file format, the information's actually not great. The format is described at a very high level, and the article critiques the specification for being vague in certain areas. Fair enough. Then of course you can always go directly to the specification, and despite the concerns mentioned in the Wikipedia article, it's definitely possible to develop an understanding by reading this document. But a picture paints 1,000 words, and by searching around for a little while, I came across this quaint GeoCities-esque page from sapp.org, which distills the spec into a very practical and very understandable form. It first tells us that the WAV file format is a subset of Microsoft's RIF specification for the storage of multimedia files. A RIF file starts out with a file header followed by a sequence of data chunks. A WAV file is often just a RIF file with a single WAV chunk that consists of two subchunks. And by looking at the diagram below, the RIF header and the two subchunks become immediately apparent. The RIF chunk descriptor describes information about the ID, the size, and the format, while the FMT or format subchunk seems to describe meta information about the sound, like what kind of audio format it is and how many channels are used, the sample rate, and a bunch of other data points. The data subchunk looks like it's mostly a container for the data, first starting with the size of the data, and then a block that contains all the raw sound information. This picture also very helpfully labels the size of each field in bytes, as well as its endianness, and the byte offset where that field should start. So at byte 0, there is a 4-byte big endian chunk ID. At byte 4, there is a 4-byte little endian chunk size, and so on. As a side note, endianness here refers to the order in which the bytes are stored in memory when you have a number that takes up multiple bytes. Big endian puts the largest part of the number first, and this is the endianness we're familiar with in the everyday decimal world. Little endian places the smallest byte first, and although confusing, this is extremely common when working with binary data. So by reading the header and the format subchunk, you get all the information you need to decode the data. Let's generate a very simple WAV file in Audacity as a test case. In the Generate menu, we'll select Tone, which would be a square wave at 0.5 amplitude lasting for 1 second. Which sounds like this. Now that we have some idea about how the information is laid out in a WAV file, as well as a file to test on, we can start to write a program that can extract that information. There are many different approaches you could take, but we're going to use a library which we've used on this channel before, called arcsecond, as well as a set of parsers specifically for extracting binary data in a package called arcsecond-binary. After creating a project directory and installing arcsecond and arcsecond-binary, we can create an index.js file and require all the libraries we need, as well as the file system and path modules. Then we can read out the contents of the WAV file. When we read a file in Node.js, we get back a buffer. This data type is node specific, but its underlying implementation is built with a standardized type called an array buffer. We can access this array buffer with file.buffer. We can see here that the file buffer is an array buffer with a byte length of 88,244 and a bunch of hexadecimal bytes. According to the image we saw, we first need to pass the rif chunk descriptor, which starts with a 4-byte chunk ID. Reading below, it tells us this should be the uppercase ASCII characters RIFF, or the 32-bit big endian number 52494646. In a binary file, the first 4 or so bytes are often referred to as the magic number, and together with the file extension, this magic number can be used to see what kind of file we might be dealing with without having to read the whole thing. So we can write a rif chunk parser using sequence of, first capturing the raw string RIFF. Next is chunk size, which is 36 plus subchunk 2 size, or more precisely, 4 plus 8 plus subchunk 1 size, plus 8 plus subchunk 2 size. Essentially, it's the size of the rest of the file from this point. It's typical to see fields like this in a binary format, because it can be used as a smoke test to make sure that the rest of the file is good. We're only 2 bytes in, and we can already check if the file is as big as it says it should be. If it weren't, we could throw an error to the user and tell them that their WAV file is bad. And since this is a 4-byte little endian number, we can parse it with U32LE. The U here refers to unsigned, meaning that we're not accounting for any negative numbers here. And although it's not specified, we can assume that the number is unsigned, since a negative size wouldn't really make any sense. Finally, we have the format, which is 4 bytes in big endian. Again, reading below, we'll see that this is in fact ASCII encoded text, which is always the word WAV in all caps. So the parser will just be another raw string with the characters WAV. Let's run our parser on the data and see if we can extract some information. Output will be rifchunk.run file.buffer. We'll check for any errors and throw them if they've occurred, and otherwise we'll print our results to the screen. And there in the console we can see the magic data, the chunk size of 88,236, and the format string WAV. And since we already know we can sanity check the file based on the chunk size, let's go ahead and do that too. We'll create another parser called rifchunkSize, which again is a U32LE, but this time we'll chain to get the resulting size. Inside the chain callback, we can check and see if the size is equal to the length of the file minus 8. If not, we'll return a failing parser with a descriptive error message, and otherwise we'll return a succeeding parser with the size. We'll replace the U32LE in the rif chunk with our rifchunkSize, and we'll see that when we run this again, it produces the same result. But if we were to change this condition so that the size doesn't match, you'll see that we now get a useful error message. Next, we can write a parser for the format subchunk. Instead of sequence of, we'll use coroutine, so that we can reference the values of the fields that we're parsing as we go. For more information about how this mechanism works, you can check out the Chain Tricks episode of the Parser Combinators from Scratch series. The first field is a 4-byte big endian ID, which is just the ASCII string FMT space. Then immediately afterwards we have a 4-byte little endian subchunk size. Next is a 2-byte little endian audio format. Reading below, we can see that if the value is 1, then the audio format is considered to be PCM, or pulse code modulation. And in short, pulse code modulation audio models a waveform as a series of samples, taken at a regular time interval. Each sample is a specific bit length, and the value represents the amplitude of the wave at that point in time. In a 16-bit per sample PCM encoding, each sample can be one of 65,536 possible values. This value, along with the sample rate, how many samples are in 1 second of audio, define how precise this audio model can be. Values other than 1 in this field represent some other, mostly proprietary form of encoding, which we won't be handling here today. Next is a 2-byte little endian number representing the number of channels. In the context of a WAV file, each channel represents one independent signal. A file with one channel is considered mono, with 2 channels is considered stereo, and so on. After the number of channels comes the sample rate, which, as previously mentioned, states how many samples per second this data represents. This field is 4-byte little endian and tends to take on very specific values. Checking the table of the sample rate article of Wikipedia, you can see that 44,100 Hz is a standard for audio CDs, and 48,000 Hz is the standard for professional digital audio equipment. Other values are possible, but these are the 2 you're most likely to encounter in the wild. Next is byte rate, a 4-byte little endian number, and in the description we can see that this is a computed value that should equal the sample rate multiplied by the number of channels multiplied by bits per sample divided by 8. We haven't passed the bits per sample field yet, but when we do, we'll be able to sanity check this value. The next field is block align, and this is 2 bytes little endian. The description states that this field should be equal to the number of channels times bits per sample divided by 8. And it also includes an interesting note. The number of bytes for one sample including all channels. I wonder what happens if this number isn't an integer. And I'm actually not sure about that, but I imagine that most audio software would simply reject a file with a bad value here. Finally, after block align, we'll get a 2-byte little endian field, bits per sample. Most commonly this can be 8, 16, 24, 32, but 16 bits per sample, or 2 bytes, is the value that I've seen the most. Now that we have all the data, we can perform some sanity checks. The expected byte rate is sample rate multiplied by number of channels multiplied by bits per sample divided by 8, and if we don't get that, then we can yield a failing parser with a helpful error message. And to be safe, we'll do the same thing with the expected block align, which should be number of channels times bits per sample divided by 8. At the end of the parser, we can return an object with all the data that we've gathered up so far and build a higher level parser, which is a sequence of first the riff chunk, then the format subchunk, and then we can take a look at the output. We see that the format subchunk is parsed correctly with a subchunk size of 16 bytes, an audio format of 1, symbolizing PCM, and 1 channel of audio, a sample rate of 44,100 Hz, and a byte rate of 88,200 Hz. Then we have a block align of 2 and 16 bits per sample. Using this information, we can write a third parser for the data subchunk. But there is a slight problem, because we don't have an easy way of parsing the information that we just got here into another parser that comes later on, at least when we use sequence of. We could use a global variable, but this isn't a very clean solution, and if we happen to be parsing multiple files in parallel, this would very quickly break down. A better way would be to use the built-in declarative state management solution of arcsecond. So if we scroll back up to the format subchunk parser, instead of immediately returning this object, let's instead assign it to a variable, and then use the special parser setData. This parser doesn't consume any input or alter the parsing state at all, but it does allow us to store some data during this specific run. That data can be later retrieved with getData in the same way, and this is how we can get data between our parsers that are not directly coupled to one another. And of course, once again, we can return the data from this function, and then scroll down to write the data subchunk parser. Again, we'll use a coroutine parser, and the first fields we need to parse are the ID, which is the ASCII string data, and then a 4-byte little endian encoded number for the size. And if all went well there, we can retrieve the data we just stored with getData. All that's left for us to do now is to actually retrieve the sound data in the WAV file. And based on all the information that we've parsed so far, we can work out exactly how much data we need. The number of samples that we need to process is the size of the data divided by the number of channels divided by the bits per sample divided by 8. We can create an array of arrays, one for every channel of audio. And then we need to create a sample parser that can read the right data size for each sample. So if we have 8 bits per sample, we can use S8, or a signed 8-bit number. If we have 16, we'll use S16LE for a 16-bit signed little endian number. And of course, if we have 32, we can use S32LE. And just to make things easier, if it's anything other than these sizes, we'll just throw our hands up and say that we can't process it for now. Next, we can loop through all of the samples that we need to collect, and every iteration of this loop, we need to collect the samples for every channel. So we can create another loop from 0 to the number of channels that we have, grabbing the sample value using our sample parser and pushing it into the correct sample array. At the end of the function, we can return the object with ID, size, and channel data. And then the final parser becomes rif chunk, followed by a format subchunk, and then the data subchunk. And for good measure, we can add an end of input as well, asserting that there is no more data after this point in the parser. After mapping the output into an object, we can console log and see the parsing result. In the terminal, we see an object with 3 keys and all of the structured data that we've pulled out of the binary file. Now, the channel data isn't shown, but if we change the console log to show the first 100 items there, we'll see what kind of data we're actually dealing with. And since this is 16-bit signed data, the ranges that each sample can take on are minus 32,768 up until 32,767. And that does seem to fit with the square wave that we generated, since we're seeing values from around 16,383 down to minus 16,383, which is almost exactly 50% of the maximum value on each side. And we generated a 50% amplitude wave. It also seems to fit that we have a lot of values around 16,383, and then all of a sudden we have negative values, exactly the kind of shape we'd expect for a square wave. So now that we've successfully read a wave file, and we've pulled out all of the interesting information from it, how can we create our own? For that, we're going to use a library called construct.js. After installing it, we can require it at the top under the name C. The primary unit of organization in construct.js is a struct. For example, the rif chunk will be a struct. And a struct is comprised of an ordered set of fields. And the first field in our rif chunk struct is the magic number, which is the raw ASCII string rif. The next field is a 32-bit unsigned little endian size. And since we can't measure that full size yet, we'll just set this to 0 for now. The last field is the format name, which is just the raw string wave. Next, we've got our format subchunk, which we'll also model as a struct. Its first field is the raw ASCII ID. That's followed up by a 32-bit unsigned little endian subchunk size, which, again, we don't know yet, so we'll just leave it as 0. Then we have a 16-bit unsigned audio format. We'll be using pulse code modulation, so we'll set this to a 1. The number of channels, also a 16-bit unsigned value, will be a 1. For the sample rate, a 32-bit unsigned little endian value, we'll use 44,100. Like our generated example, we'll be using 16-bit samples, so our byte rate is going to be the sample rate multiplied by 2 for the 2 bytes. Block align will be 2, and our bits per sample will be 16. Now that we have the whole struct, we can properly compute and set the size field. We can get the total subchunk size by calling compute buffer size, which gives us back the number of bytes taken up by this struct. And then we can get the subchunk 1 size field on the struct and set it to the total size minus 8 bytes, as per the description document. And that just leaves us with the most important struct, the data subchunk. It has an ASCII string ID of data, followed by a size that we don't know yet, and finally the data itself. For this field, we'll specify an array of 16-bit signed integers, just like when we were parsing using arcsecond. Now, we need to be able to build a sample array that models a wave. To keep things simple, we'll replicate our example of a 440 Hz square wave. We can create an empty array for the sound data and a variable called isUp, which will keep track of if our wave is at the top or the base. Then we can loop from 0 to 44,100 in order to create 1 full second of audio. Every wave has a frequency, and we're aiming for a frequency of 440 Hz. That means that the wave goes from the top to the bottom and back again 440 times per second. And since we have a sample rate of 44,100 samples per second, that cycle will take around 100 samples to complete. After around 50 samples, we need to switch from outputting the top part of the wave to outputting the bottom part of the wave, and back again after another 50 samples. And we can do this quite easily with a modulo operation on the I variable. If I modulo 50 is 0, then we'll flip the value of the isUp boolean. The value of the sample will be a positive value when isUp is true, and a negative value when it's false. We can use the same value of 16,383 that we saw when we were parsing the example, which represents about a 50% volume. Finally, we can assign the value to the corresponding index in the sound data array. Now we can set the data field in the data subchunk struct to what we just created, and set the field size to be the length of the sound data multiplied by 2. We can bring it all together with a top-level struct that defines the wave file, with a field for the riff chunk, format subchunk, and data subchunk that we created earlier. And all that's left to do now is to write the new wave file, getting the data by calling filestruct.toBuffer. Let's give this a listen. Alright, that sounds pretty much identical to the example wave, which is a good thing. And we can prove that we are in fact creating a different file by doubling the amount of samples that we need to count before switching isUp, or in other words, halving the frequency. This gives us that same A note, but an octave lower. And with that, we've successfully understood, parsed, and created a binary file format from scratch in pure JavaScript. And as always, the code for today's episode is on GitHub at github.com/lowleveljavascript, and you'll find links to further reading in the description. Thanks to all the amazing patrons of this channel. If you'd like to support these videos, you can become a patron yourself by visiting patreon.com/lowleveljavascript. $5 per video gets you these videos just a little bit earlier than everyone else, and every tier gets access to scripts and other updates that you won't see anywhere else. Thanks for watching, and I'll see you next time.